Hello everybody. Today we're going to be talking about how to find the area between two curves using an integral. So the first shape we're looking at is a relatively simple triangle, and just looking at it you can sort of see what the area is going to be using geometry. Area of a triangle equals 1/2 times base times height, and in this case we can see that from 3 to 1 it's 2, and from here to here it's 2, and we know that because y equals 1 right there, and when y equals x, and this is x equals 3, so this must be 3, 3. So from 3 to 1 is 2. And that gives us 1/2 times 2 times 2, which we know is 2. So this one's relatively simple, but they're not all going to be this simple. In some cases, we'll have a curve. There's no readily available geometric equation to find the area of this shape, so instead we're going to use integrals. So let's take a look at our formula here. What we're looking at here has multiple parts. We'll start with the from A to B, which in this case indicates the leftmost part of the region that we're trying to find the area of, and the left and rightmost parts. A being the left and B being the right. These are notably the x-coordinates of these points. The f of x and g of x represent the equations for the lines that bound the region that we're looking for the area of. And of course the dx is just taking the integral. So what's functionally happening here is we're finding the integral of f of x, which is always going to be the top equation, and that is all of this area here. And then from that we are subtracting the integral below g of x, which is the bottom line. So we're taking away this area. So we're finding, what's left behind after that subtraction is the area that we're looking for. So with that in mind, you can reliably count on your f of x being the line that is higher up, at least if you're taking integral d of x. If you're taking integral d of y, it gets a little more complicated. But for now, we know that this blue line here, y equals 4x plus 16, is going to be our f of x. So our integral is going to start 4x plus 16 and minus, and then our g of x is the bottom red line. So 2x squared plus 10 dx. And then we also need our a and our b. And as I said, that is the x coordinate for these two points that make the leftmost and rightmost boundaries of the section. So to find these points of intersection, we're going to have to set the equations equal to one another. So we'll do that down here. We'll just get everything on one side, and then factor. You can do this in the way of your choosing, but generally, I like to think of it as what's going to add to multiply to -3 and add to -2 in this situation. This gives us our x-coordinates of those intersection points. And we can sort of logically, using the picture here, figure out that this -1 is going to be on the left, and this 3 is on the right. And of course, those are just the x-coordinates. We don't need to find the y-coordinates in this situation, but you can by plugging those back into the original equations to solve for y. So this is going to be from -1 to 3, from left to right. So now we can integrate. We're going to start that by just sort of simplifying, combining like terms and such. So -2x squared plus 4x plus 6 dx. So now we're going to take this integral using basic power rules of integration. So this x squared becomes an x cubed, and then we divide by 3. X becomes x squared, and divide by 2, but since that's a 4, we'll just simplify. And 6 just gets an x added on. Now we're going to put in our 3 and our -1. So we'll start with the 3. 3 cubed is 27, but divided by 3, it's just 9, and times 2, that's 18. 3 squared is 9, 18 again, plus 6 times 3, 18. So immediately we recognize that these two 18s are going to cancel, but we'll leave it for now. Put a -1 in, we get 2/3 plus 2 minus 6. So if we do some combining, we're going to get 18 minus 2, since this distributes, plus 6, which is 22, and still minus 2/3, which gives us 21 and 1/3. And that is going to be the area between these two curves. All right. Have a nice day, everybody.